Good morning, good afternoon, good evening to all the ATM seminar participants. And thank you for coming to this session, which is on complexity science, analytics, and big data for air traffic management. We have two very interesting presentations from very budding scientists, Ramon and Loic. So first, we have Ramon, who is a data scientist at the EUROCONTROL Innovation Hub, a very well-known face in the ATM community. His academic background is in aerospace engineering, and he did his master's in computational applied mathematics from Autonomous University of Barcelona. In 2019, he obtained PhD in aerospace science and technology from TU Catalonia, and his research interests include optimization algorithms, machine learning, and multi-agent reinforcement learning, all of them applied to improve the air traffic management system. And Ramon will be talking today about a machine learning approach to predict the evolution of air traffic flow management delay. Quite a very interesting topic, Ramon, and the floor is yours. Also, a quick request to all the participants, please type in the name of the presenter when you are putting the questions in the Q&A, so we know that this question is for a particular presenter. Thank you, Ramon. Please go ahead.
Thank you for the introduction, Samir. I am going to present the results of one of the projects that were executed during the first wave of InnoLabs, powered by the EUROCONTROL Innovation Hub in 2020. The objective of this project was to predict the evolution of the air traffic flow management delay of a regulated flight. But before starting, I would like to acknowledge all my co-authors, Brice, Camille, Peter, and also Darren, because they worked very hard in order to make this possible in only 6 months. This is the outline of the presentation. I will start by introducing the problem that we wanted to solve. Then I will describe the architecture of the model that was a neural network. Then the input features that the model is using to make the predictions. Then I will present the data that we used to train the model on past traffic, and then some initial results. And finally, I will conclude and give some future work. As you know, in Europe, the most common air traffic flow management measure used by the network manager to balance demand and capacity consists of imposing air traffic flow management regulations at specific traffic volumes during specific periods of time. These regulations limit the maximum rate of aircraft that can enter the traffic volume in order to ensure that the capacity is never exceeded during the regulated time period. When a regulation is defined in a traffic volume, a list of air traffic flow management slots is created from the start time to the end time of the regulation, and the width of each slot is determined by the maximum rate. Then, all flights that plan to enter the traffic volume during the regulated time period are assigned to a free slot in a first-come, first-served basis. Some of the regulated flights need to depart later in order to enter the traffic volume at the assigned slot. That is, they need to be delayed on ground. And this is what we call the air traffic flow management delay. In this slide, for instance, you can see a list of flights, regulated flights, and each row corresponds to one of these flights. Then each column shows some information of the corresponding flight, like the call sign, the departure airport, the destination, etc. And highlighted in red in the very last column, you have the current air traffic flow management delay. But this is just the picture at a given time, and it's very likely to change as the day evolves. In fact, the air traffic flow management delay that is assigned to a flight changes with time. And this variability of the delay stems from the mechanisms used by CASA, that is the Computer Assisted Slot Allocation System, to manage the slots of the different regulations. And it's out of the scope of this presentation to present the details of how CASA manages the slots, but you can find more details in the paper. In this presentation, I just want you to remember that the air traffic flow management delay is dynamic and that may fluctuate a lot. Unfortunately, the information of the evolution of the air traffic flow management delay is very limited for the airspace users. In fact, they only know the current air traffic flow management delay, but they have no means to predict the evolution. And this was the objective of this project, to develop a set of indicators which were requested by the airspace users about the evolution of the air traffic flow management delay of a regulated flight. Fortunately, we have plenty of data about the air traffic flow management delay of each regulated flight from the time that it was regulated to the actual takeoff time. In other words, we know the history or time series of all the delays that were regulated. And for this reason, we trained a neural network with a lot of historical data using machine learning. Each example showed to the neural network during the training process corresponds to the history of messages received from a particular regulated flight and the associated actual delay at takeoff time. This is our target, the value that we want to predict with the neural network. As you can see in this screenshot of the new HMI with these delay evolution indicators, we developed 3 different indicators. First of all, the trend of the delay, which shows the probability that the delay will increase, decrease, or stay stable, the probability that it will decrease to 0, and the predicted delay in minutes. These 3 indicators are computed by independent models that I will present in the following slides. Before explaining the model, we need to understand the data that we receive from each regulated flight. Each row in this table corresponds to one message that was received from an hypothetical flight. This is just an illustrative example at a given time, which is the first column. And each column shows a different attribute or characteristic of this flight at a particular time. Some of these attributes are static, like the departure or destination airport, while others are dynamic, like the air traffic flow management delay. Let's imagine that we are at 10 a.m., the third row in this table, and we want to predict the actual ATFM delay at takeoff time. And we don't know it because it's in the future. As any time series prediction, our prediction is conditioned on the whole history of the messages that were received from this flight since midnight. That was the initial flight plan, the first message received from this flight. We will call xt the vector of features extracted from the T message of each flight, where T goes from 1 to capital T, the sequence of messages received from this particular flight. At a given time, a flight could be subject to more than one regulation. Therefore, we may have a sequence of regulations within each message. In this example, for instance, at 1 a.m., this flight was subject to 2 regulations. And we can make it even more complex because each regulation can be divided in several periods with different rates. For instance, regulation 2 of the message that was received at 1 a.m. is divided in 2 periods, one from 12:50 to 1:30 with a rate of 45 aircraft per hour, and then from 13:30 to 14:10 with a rate of 30 aircraft per hour. Summing up, we make predictions based on the sequence of messages, and each message may include a sequence of regulation, and each regulation may be defined by a sequence of periods. So this is a hierarchical structure. For this reason, our model is based on recurrent neural networks and hierarchical neural networks. For those that are not familiar with machine learning, a recurrent neural network is a special architecture very good at learning sequences from patterns from sequential data. There are several types of recurrent neural networks, and in this paper we use the GRU because they are much more simple than LSTM. They have less parameters, meaning that they are easier to train, and typically they showed very similar performance. Essentially, a recurrent neural network receives a sequence of input vectors, xt from T1 to capital T, and optionally initial hidden state, H0, and generates a sequence of hidden states where the sequence of hidden states has exactly the same length as the sequence of inputs. The hidden state at a given time depends on the hidden state at the previous time, as well as the corresponding input vector. This is why it's called a recurrent neural network. I will not enter into details. You have more details into the paper, but it's important to remember that the recurrent neural network has a set of parameters that are unknown and that are adjusted during training to accomplish a given task. Here, to predict the evolution of their traffic flow management delay. Remember that the data of a given flight follows a hierarchical structure. So the model performs the predictions from a sequence of messages. And each message may include a sequence of air traffic flow management regulations, because a flight might be subject to more than one regulation simultaneously. And each regulation may be composed of several periods. Okay. Therefore, the model works as follows. First, each regulation of each message in the sequence, the model tries to summarize the information of all periods in just one vector. Okay. But in the data, we observe that most of the time, the regulations are composed by just one period, as you can see in this histogram. For this reason, and in order to simplify the model as much as possible, we selected the data for the period P, such that the flight enters the regulation R in the message T. Okay. We will call this period period Q. Then we concatenate the information of this period, the period Q, with the generic information of the associated regulation that we will call XTR. At this point, we have successfully removed one of the levels in the hierarchy, simplifying the data, the periods. And the features of each regulation include now a summary of all the periods. For a given message, however, we still have a sequence of regulations that we need to summarize in just one vector. In this case, we feed the data for the sequence of regulations ordered by entry time, by estimated time over, into a bidirectional GRU, which processes the sequence in the two directions, forwards and backwards. And then we take the last hidden state of the two directions, which summarizes the sequence of regulation in just one vector. Finally, we concatenate the vector, summarizing the regulations with the features of the corresponding message, like the departure, the destination airports, the airline, etc. And then we feed the sequence of messages into a GRU. From the sequence of hidden states that are generated by the GRU, we are only interested in the very last one, because it's the one that captures the whole history of the flight. Summing up, this architecture summarizes the periods of each regulation into one vector, and then the regulations of each message in one vector, and then feeds the sequence of message into a recurrent neural network to end up with a vector, HT, that summarizes the whole history of the regulated flight. Each one of the components of this model has a set of parameters or weights to be trained during the training process from the data. And it's important to remark that each one of the indicators that I will show right now is computed by a different copy of this architecture. The only difference among the different models which predict the different indicators sharing the same architecture is in the very last layer of the model, and also in the loss function that we used to train the parameters or weights. Now I'm going to present the different variants of the model. The most straightforward variant of the model predicts the value of the actual delay, or the last ATFM delay in minutes, which is a positive value. And in order to ensure that the output is higher or equal than 0, we use a rectify linear uniform as activation function of the very last layer. This is a basic regression problem, and the model is trained to minimize the mean absolute error between the actual delay at takeoff time and the predicted ATFM delay, the current one. But this model works fine, but it does not provide a measure of uncertainty. And this is why we also designed a second variant of the model, which predicts the distribution of the last ATFM delay. But first, we need to know which is the distribution that better describes the ATFM delay. As you can see in this slide, the actual ATFM delay most of the time is 0 and presents a very long tail to the right. And this distribution is known in the literature as zero inflated Poisson distribution. Fortunately, this spatial distribution can be parameterized with only two values: rho, that is the probability that the value will be 0, and lambda, which is the rate of the associated Poisson distribution. So the second variant of the model, which predicts the distribution of the ATFM delay, is identical to the basic regression model. But instead of predicting just a scalar, a value, the actual ATFM delay, it predicts the two parameters that describe its probability distribution, rho and also lambda. Rho is a value between 0 and 1, and because it's a probability, and this is why we use as activation function a sigmoid. And lambda is a value higher than 0, and this is why the activation function of the associated feed-forward neural network is a rectified linear uniform. This slide shows how the shape of this distribution changes as we modify the two parameters. The figure in the left shows the effect of modifying rho for a given lambda, and the figure in the right shows the effect of modifying lambda for a given rho. And a very nice characteristic of this distribution is that the expected value can be computed as 1 minus the probability of 0, that is the probability that will not be 0, multiplied by the expected value of the associated Poisson distribution. So it's very easy to compute the expected value. The third and last variant of the model predicts the trend of the delay. That is, it tells us the probability that the delay will increase, will decrease, or will stay stable. In this work, we consider that the delay increases if the last ATFM delay is higher than the current +5, decreases if the last ATFM delay is lower than the current -5 minutes, and stays stable otherwise. This is a classification task because we have 3 possible classes, and the model has to determine in which one of them the ATFM delay trend belongs. However, this is not a typical classification task because our classes have an order. We should not penalize in the same way a model when the actual value is decrease and the model predicts increase, which is a very bad prediction, that if the actual value is decrease and the model predicts stay stable, which is a wrong prediction, but is not that bad. This is why we addressed the problem as an ordinal regression task, in which the model has to learn the location of k-1 cut points, where k is the number of classes, in this case 3, and the location of the cut points determine the shape of the distributions corresponding to each one of the classes. Okay, and then the model predicts y ordinal, as you can see in this picture, and y ordinal determines the probability to belong to each one of the classes according to the locations of the cut points. Similar to the previous model, the weights and also the cut points of the model are trained in order to minimize the negative log likelihood of the prediction. As I said before, the model makes the predictions from the sequence of messages sent by a regulated flight, from the submission of the initial flight plan to the current time. And for each one of these messages, several features are extracted from the hierarchical data. These features can be classified in 2 different groups: categorical features and numerical features. In the categorical features, we have departure airport, destination airport, the state of the flight, the traffic volume where the regulation is applied, the geographical entity associated to the traffic volume, the type of geographical entity that could be an airspace sector, could be an airport, could be a group of airports. Also the reason of the regulation, like weather, ATC capacity, as well the airline, and many others. Essentially, categorical features are those that take discrete values. And then we have the numerical features that take continuous values, like the time to the start of the regulation, the current ATFM delay, which of course is a very important predictor, the hour of the day, which could be considered categorical as well. and also the number of regulations. All categorical features are converted to a vector of numbers, okay? Because we cannot work with strings. We need to convert to numbers by using an embedding layer, which parameters are learned during the training process. Then, for the numerical features, several transformations are possible. For instance, some of the features require a missing indicator in order to tell the model that we don't know this feature, that it's missing in the data. Some other features followed a very skewed distribution, not Gaussian at all. And we need to make a power transformation, like a box Cox, for instance, before performing a classical standardization. Finally, there are other features like the hour of the day, which have a cyclic nature. And for these features, we compute the cosinus and the sinus, making this cyclic transformation. So we convert one feature into two features. And finally, some other features just require a simple normalization. For instance, min max, or divided by a factor, for instance, 10 or 100. You can find the whole list of features classified by their level in the hierarchy. So message, regulation, or period of a regulation, as well as the type of transformation that was applied in the paper. The features that I presented in the previous slide were generated by combining two sources of data. First of all, enhanced tactical flow management system, or ETFMS, flight data messages, what we call the EFD data, of all flights that were regulated during 2019. And from this data, we extract the features like the departure and destination airport, the airline, the estimated off-block time, the ATFM delay, and the taxi time, etc. We receive an EFD message whenever the data of the corresponding flight changes. For instance, when the most penalizing regulation changes for that flight, when the ATFM slot and therefore the ATFM delay changes, etc. So we have plenty of messages for each one of the flights, which is the data that we use to fit the model and make the predictions. And then we also used the evolution of the corresponding air traffic flow management regulations during 2019, which show the time of the activation, the regulation rate, also the reason of the regulation, and the start and end time, among other attributes that I am not showing in this slide for the sake of clarity. The model was trained by using 300 random days of 2019. Then we used 20 days for validation and hyperparameters tuning, and 40 days to assess the performance of the model on unseen data. And we trained the model during 3 epochs, which means that we showed the whole training set, the 300 days, 3 times to the model. Each model has around 2 million of parameters, and we need 7 hours to train the model using a normal NVIDIA Tesla K80 GPU that was kindly provided by MUAC. This is just an example for one of the flights. So in the first column, you have the time to EOBT. This is the look ahead time of the prediction. Then in the second column, you have the state of the flight. FS, and this is very important, means that the flight is regulated, but that the slot has not yet been allocated. And SI means that the flight is regulated and it has a ATFM slot allocated. Then in the third column, we have the ATFM delay according to CASA, so the current ATFM delay. And this is the information that the airlines have nowadays. And then the last columns, the last columns are the indicators provided by the model. So the first column, Y basic, is the ATFM delay as predicted by the model at takeoff time. So we are trying to predict the delay of the very last row at takeoff time. And then rho is the probability that it will decrease to 0. And then in the last 3 columns, we have the probability that it will decrease, stay stable, or increase. And we can observe that for this particular flight, 4 hours before EOBT, the model was very confident that the current delay, that was 79 minutes, would decrease to 12 minutes, but that will decrease to 0 with only 25% of probability. But the model was very confident that it would decrease because, as you can see, the probability that it will decrease is around 98%. And we can observe that actually around 7 minutes or 2 minutes before EOBT, the delay decreased to 19th, which shows that the model 4 hours in advance was already quite sure about the prediction. This slide shows in the left the errors of the current predictions. That is, we take the current delay, we assume that it will not change, and we compare it to the actual delay, the delay at takeoff time. And this is the mean absolute error in the test set. So the, I think, 40 days that we used for assessing the performance of the model on unseen data. And then in the plot in the right, you see exactly the same metrics, but for the machine learning model. The results are shown as a function of the time to the calculated off-log time in hours, okay? So the look-ahead time, and as a function of the state of the flight. Remember that FS means that the slot has not yet been allocated, and SI means that the flight is regulated and the slot is allocated. And we can observe that 4 hours or more before COBT, the model is able to reduce the current error from 26 minutes to 9.4 minutes, let's say 10, which represents around a 60% decrease in the prediction error. And then if we move to 2 to 4 hours before COBT, we are able to reduce the error from 13th or 19th minutes to 7.6 and 10 respectively, which represents a 50% increase, improvement. Then from 1 to 2 hours, we decrease the error from 9 to 6 minutes. And 1 hour or less before COBT, we see that there is no reason to use this model because the current predictions are already very good. The mean absolute error is 4 minutes. The delay is very stable. And our benefit is only 0.2 minutes. So it's residual, the benefit of the model. There is no reason to use the model when we are very close to COBT. And in fact, at this time, the airline has no time to react. These are exactly the same results, but for the Poisson regression model, okay? Using the mean absolute, the expected value of the distribution predicted by the model. Because remember that this model is not predicting a single value, but a distribution. And we can observe that the results are almost identical, slightly worse, of course, because this model is not trained to minimize the mean absolute error, but the negative log likelihood. So this is why are not exactly the same, but are very similar. And finally, this slide shows the results for the ordinal regression model. But in fact, the name is a little bit confusing because it's not performing a regression, it's performing a classification. It's trying to classify the trend of the delay into decrease, stay stable, or increase. And here we are showing the results in the same way. So in the horizontal axis, you have the time to COBT, the look ahead time, and in the vertical axis, the state of the flight. So FS or SI. And within each cell, we plot a confusion matrix. Okay. If you sum all the values of this all confusion matrix, it's 100. So the number that you see in each cell, it's the number of samples of the whole test set that belong to that cell. And the values in the diagonal within each confusion matrix are correct predictions. And of diagonal values are wrong predictions. We can observe that the model most of the time is correct. So it performs good predictions. And when it performs bad predictions, typically the value that is assigned is the one in the nearest cell. Okay. But we can also observe that the model has some difficulties to predict when the delay is going to increase. So the model is very good at predicting when the delay is going to decrease or stay stable, but it has difficulties to predict when it is going to increase. And the reason is that, as I showed you before, the last ATFM delay typically follows a zero inflated Poisson distribution. And most of the time, the delay either decreases or stays stable. So we have few samples in relative terms where the delay has increased. So it's a very unbalanced data set. And the model is biased to predict decrease and stay stable. Of course, we could solve this issue by giving more weight to the difficult examples, so to the examples where the delay increases. But this is something that we are still working on. So in this paper, I presented a generic model inspired by hierarchical architectures and also recurrent neural networks that is able to provide several indicators of the ATFM delay evolution of a regulated flight. So the predicted ATFM delay, the predicted trend of the ATFM delay, as well as the distribution. These indicators were designed to improve the situation awareness and also the decision-making for the operations. And the initial results from data of 2019, so not COVID period, shows that the model improved the accuracy of the current delay predictions that, well, in fact, there are no predictions. We just received the ATFM delay and we assume that it will not change between 30 and 63%, depending on the look ahead time and the state of the flight, as I showed you in the previous slides. And we also observed that when approaching the COBT, the calculated offload time, when we are very close to takeoff, the benefits are marginal and there is no reason to use this model. In future work, we must consider explicitly the effect of the overall traffic network in the predictions, because this model assumes that this flight is alone in the network. Maybe it's considering some effects of the other agents in the network implicitly in the data, but not explicitly. And we could explore other architectures like graph neural networks to improve the performance of this model. And of course, something that we are working on and that is very important is to improve the performance of the trend classification model. That is the ordinal regression, the one that is trying to classify the trend into increase, decrease, or stay stable. Because we observe that it has difficulties to predict increase of delay. And as I said before, we could do this by giving more weight to the increased class when sampling during training, or also in the loss function, meaning penalizing the model when it makes mistakes on these classes. That's all. Thank you for your attention, and I will be happy to answer to your questions.
Thank you, Ramon. Quite an interesting presentation. Very interesting. The topic was covered, especially now with ATFM becoming a major challenge for the airlines. I think this research could be very useful for them to help them predict well in advance the CTBOT and other timings that are useful for them. So the floor is open for some questions. Please feel free to post your question on the Q&A. And while we are waiting for some questions, maybe Ramon, I can start with some clarification and questions.
Yes, sure.
So there are some very well-known models in the literature on ATFM actually, but I didn't see any comparison in your paper with those models and how your models scale up with them. Can you elaborate a little bit on that?
Yeah, I think that here the problem is that most of the models that you can find in the literature are trying to make predictions, but not considering the history of the ATFM delay, just trying to predict the last ATFM delay from the beginning. And this is because the data is not publicly available, meaning so in DDR you can download the last ATFM delay, but you cannot download the first ATFM delay or the second ATFM delay. You don't know the evolution. And this is why it's very difficult to compare our model with other models in the literature, because in fact, we are solving a different task. The task that we are solving is, okay, given the time series of the ATFM delay so far, from the time that this flight was subject to one of the regulations, let's try to predict how it will evolve. So we can only compare our model with the baseline, that is the CASA predictions.
Understood. Is that data publicly available, or you need a DDR account for that?
No, unfortunately, this data was extracted from the ATFMS, and yeah, the only data that is available about ATFM delays is the DDR data, as you know.
Right. Right.
which only shows the last picture. In fact, it shows only what we are trying to predict.
Right. Actually, the last comment that you made was very interesting about the consideration of other actors in the air traffic management network and the possibility of using a graph neural network kind of structure, which can incorporate other delay impact measures on the evolution of ATFM delay. So how do you propose or think about going about that? Can you elaborate a little bit on that?
Yeah, this is a very good question. When we started this project, we had in mind several models. We said, okay, we could start by decision tree because it's the most straightforward. It's very easy to implement. You don't need to do feature transformations, these embeddings or feature scaling. It's straightforward. Yeah. But when we said, okay, in fact, we are dealing with a time series prediction problem. So we have sequential data and we should use recurrent neural networks. And then we realized that at the end, a flight was not alone in the network, that we could explore these graph neural networks where, for instance, each agent could be a flight and flights belonging to the same regulation could be connected, okay? Sharing some information, some features. I still don't know why this is the idea, but the problem is that we had only 6 months to perform this project and was not realistic to go for this approach. So we selected the intermediate one, neither the most straightforward, that is a decision tree, nor the most complex, that is a graph neural network.
Right.
But of course, it would be very nice to explore this in the future, because I believe that making this kind of architecture could really boost the performance of this model. I'm pretty sure.
Certainly. One interesting thing that you mentioned, that the flight may be subject to more than one ATFM measures, right? Yeah. So did you try exploring that? Is the model being able to predict that, which ATFM measures is applied to?
Wow. Hey. In fact, the ATFM regulations are now an input to the model, predicting which regulations could appear, could count this flight, could be also an interesting topic for future work. Why not? I'm pretty sure the model is doing this implicitly, no, right? So I have this regulation, now I have this other regulation, probably I will be subject to this other regulation. But we don't know. As you know, neural networks are black box models, so it's very difficult to interpret them.
Yeah, actually, this is where I was coming from, that the explainable AI part, understanding which part of this black box the machine learning is focusing on, which particular regulation it is more giving weight, that will be very interesting to see.
There are some methods based on gradients, for instance, or feature permutations that we are exploring in another project that I will present tomorrow. But in this project, we are not doing this because, as I showed in the presentation, the architecture of the input data is very complex. So it's hierarchical. We have several levels that we need to summarize in vectors. And it's not straightforward to make this gradient computation to see which one of the features is the most important. But I believe, and this is just my hypothesis, is that some of the features are not really used by the model, like the taxi time. You know, in order to predict the evolution of the ATFM delay, maybe the taxi time is not important. I don't know. So as you said, the only way to know this is to make this feature importance analysis, which for this kind of models is not straightforward.
Yeah, I understand. But very exciting work, Raman. Very exciting work. I think this research has a lot of potential, not only for airlines, but of course, in the collaborative decision making. Having such a system will play a very important role to manage the delay and to make the flights push back at the right time.
Thank you, Samir.
Okay, so wonderful. Thank you so much. You can always send an email to Ramon for questions and also PCC me so that I can keep a record of that. And we can close this presentation. And we have our next speaker about to be ready. So Ramon, if you can unshare your screen, that's wonderful. Excellent. So our next presentation is from ENAC. So we have Loic, who is doing a PhD at ENAC with Daniel, and his research interests are in machine learning and application to air traffic management. And their research topic which they are presenting is about predicting air traffic congested area with LSTM network. Quite an interesting topic. LSTM is a very hot area, especially in predicting the time series sequential data. And I'm sure we will have a lot of things to learn from you, Loic. Your floor is yours. Please go ahead.
So thank you very much for the introduction. So I will be presenting my work entitled Predicting Air Traffic Congested Areas with Long Short-Term Memory Networks. This work was advised by Daniel Delahaye and Nida Alboinaya. So I will first do a quick introduction and present some background material about complexity metric and sequential models, and then present our framework and the results. And finally, I will conclude and provide some insight about the future works. So first, a little bit of context. So the air traffic management in the en route airspace can be divided into two main roles. So first, the air traffic flow and capacity management that is looking at occupancy problem. Its goal is to balance the demand with the capacity. And so what that means is that for each sector, there is a limited number of aircraft that can cross the sector in a given time frame. And so the objective of the ATFCM is to ensure that the actual demand will never be higher than this capacity. And on the other hand, we have the controller, the air traffic control by itself, that is looking at proximity problems, which goal is to ensure the separation of aircraft, to monitor the trajectories for conflicts, and then act on the trajectories to solve the conflicts. So what we can see here is that there is a gap between the strategic part of air traffic management, the ATFCM, and the tactical part, the air traffic control. So what I mean by a gap is that even if the demand is balanced with the capacity, it is still possible that due to a special situation in the trajectories, some hotspots can appear at the control time and leads to a difficult situation from the control perspective. So to address this gap between ATFCM and ATC, there is a concept introduced by Cesar called extended ATC planning. So this function, this EAP function, will rely on automation tools to improve the communication between local flow management position and controllers, and provide information to help take early measures to mitigate these hotspots. And so the high-level objectives of this EAP function is to reduce delays, reduce the number of ATFCM regulations, and enhance the safety. So if we consider this problem of bridging this gap between ATFCM and ATC, we can split this problem into two sub-problems. So first, the prediction of the congested areas tens of minutes before the formation, and then the mitigation of this congestion by providing appropriate early actions. So here in this presentation, I will only focus on the first problem, the prediction of the congested areas. So the approach that we have chosen is to rely on machine learning techniques and more precisely on encoder-decoder LSTM framework to integrate ATFP, so air traffic flow prediction, from in one hand, and on the other hand, an interesting complexity metric. So I will detail of this all these materials in the following slides. So we will place ourselves in a time horizon of 40 minutes before the aircraft cross the sectors. And in this time horizon, the uncertainties are too high to predict which trajectories will be involved in which particular conflict. So this is due to the fact that even if we can know with great precision the 3D trajectory that will be flown by an aircraft, there is a great uncertainty on the time at which the aircraft will flown this particular point. This is due to various sources of uncertainty, such as weather uncertainties. So this is why we need, for this time horizon, to take a more global approach by looking at these hotspots or these congested areas rather than precisely predicting conflict and solving conflict. So to address this problem of congestion prediction, we can summarize the existing approaches in the literature into three families. So first, there are the conflict detection tools, such as medium-term conflict detection tools. So these tools rely on probabilistic models to predict conflicts, and then to create what-if scenarios to give information to the controllers. But they are more focused on time horizon of 20 to 30 minutes. And as I just explained, since we can't predict the precise conflicts that will appear, we can't rely on this type of models. Then we have the air traffic flow prediction approach that focuses on more aggregate models rather than individual trajectories. So they rely on a probabilistic model using modeling the flow as networks, but there is more recent implementation that rely on machine learning to predict the aircraft count. So the aircraft count, or the traffic density, is the number of aircraft that cross a sector in a given time interval. And the problem with this aircraft count is that it cannot describe the real perceived complexity. For example, here we have two situations with the same aircraft count, but the complexity on the right situation is higher. So this is why we will also focus on air complexity metrics that are trying to quantify the difficulty of the traffic situation. So congestion is defined as a situation where a set of trajectories strongly interact and will lead to potential conflicts and require high monitoring from the controllers, because from the controller perspective, the difficulty is not to solve a conflict, but to monitor the aircraft to know if they should act on the trajectory or not. And so the air traffic complexity is a measure of this difficulty that a particular traffic situation will present to air traffic control. So the goal of complexity metric is to quantify the complexity of a traffic situation. So this complexity will be linked with various factors, such as the workload of the controller, the conflict probability, or the geometry of the traffic. But the problem with the workload is that it's really difficult to quantify, to measure. It's really dependent on human factors aspects. And it's mainly a very ill-posed problem. So to evacuate the difficulty of precisely defining the workload, we will focus here on a pure intrinsic complexity metric that will only rely on the geometry of the traffic in order to really quantify the complexity of the situation without any link with the system that is actually controlling the traffic. And so to achieve this goal, we will use a complexity metric based on linear dynamical systems. So I will quickly explain the function of this metric. So here we have an example of a traffic situation that is centered on an aircraft, and we consider a neighborhood of this aircraft with all the other aircraft in this neighborhood. So we have the position in the matrix P and the velocity of the aircraft in the matrix V. And then we will consider the linear D-matrix system that will be the closest to this given data, closest in the sense of the least squares. And we can then compute this matrix A and vector B of the linear dynamical system. And what we are interested in is the eigenvalues of the matrix A that really encapsulate the behavior of this linear dynamical system. And then our metric, our complexity metric, will be defined as the sum in absolute value of the negative real parts of the eigenvalues of the matrix A. So why is that? So this is because the eigenvalues with negative real parts correspond to converging behavior, while with positive real parts, it will correspond to divergent behavior. So what our metric is really quantifying is the level of convergence in the considered traffic situation. So then I will present the sequential models and also the dataset that is used in our experiments. So here we will use recurrent neural networks since we are dealing with trajectories, and that recurrent neural networks are well suited to process sequences of variable lengths, so including trajectories. So the basic idea of RNN is simply to use the current input and the output of the previous time step in this linear transformation. Then there is an activation function to produce the current output. So this is recurrent because we use the previous output as an input for the next time step. So there is very many variants of recurrent neural networks and many applications. So here we will only focus on long short-term memory. So I will not detail the Lstm layer, but the main idea is that there is a cell state that is a memory of the layer, and at each time step, the cell state is updated with new information from the current input, and then this cell state will be used to produce the output of the current time step. So in our framework, we will also use convolutional layers, so more precisely one-dimensional convolutional layers. So the idea of this layer is that we have several filters that each have a kernel with learnable parameter. And so the kernel will go through all the time steps and combine the information from a small time horizon. So the objective of this convolutional layer is to help the network to extract local information from following time step in order to help the full network to have access to information of dynamical information rather than just looking at each input one after the other. So now the data set. So this is we will use a data set of trajectories. So a trajectory is a sequence of aircraft states. So what is a state? Here we define the state by this information. So a timestamp, the aircraft ID, then the position of the aircraft, latitude, longitude, altitude, and the speed of the aircraft, the speed vector of the aircraft. So the ground speed, the heading, and the rate of climb. So we use a data set of 8,000 simulated trajectories over the French airspace. So these trajectories are spread along 3,000 time steps. One time step represents 15 seconds, so it's almost 1 day of traffic. And then we split this dataset into 2 parts, so 2,000 sequence for training and 200 sequence for validation. So the sequence lengths are 160, so it corresponds to 40 minutes. So that means that for training, the network can see the last 40 minutes of traffic, and then it has to predict the next 40 minutes. And so we define a supervised learning regression task. So the goal of our network will be to take as input these sequences of aircraft states and then predict the value of the complexity that I have just presented in the next 40 minutes. So the inputs of the network are defined as follows. So for a given time step t, we have a set of aircraft states, state 1, state 2, etc. And then we concatenate all these states in a vector xt, and we can define our input sequence xt0 as the sequence of this xt of the concatenated states. And so this sequence is of length 160. Then to define the output, the target output of the network, we define n by n grid, n by n matrix over the airspace that is covering the airspace in longitude and in latitude. And in each value, each element of this matrix is defined as the maximum value of the complexity metric inside the given cell. So this is, in fact, the worst case in each given area of the airspace. And so our input sequence xt0 will be associated with the output matrix ht0 plus tin, so this is the length of the input sequence, plus the t-pred, so this is our time horizon of prediction, which is equal to 40 minutes. So now I will present the encoder-decoder network by itself. So it is composed of 2 parts, an encoder part in the left and a decoder part on the right. So this kind of architectures are taken from automatic translation tasks. So the objective of the encoder network is to take as input the input sequence of aircraft states and to compute an embedding vector that will aggregate all the information from the inputs. And then the decoder network will have to generate the whole sequence of our matrix HT from the current time to 40 minutes in the future. And here we use a technique called teacher forcing. So what that means is that during training, the decoder network receives as input the true value that it should have predicted in the previous time step. And during inference, since we don't know the true value, we simply use the prediction of the network as input for the next time step. So here is a summary of the full framework. So we have in the left our data set composed of 8,000 simulated trajectories, where the xit are the state vector of the highest trajectory at the time t. So first, we compute the complexity metric of the trajectories. For each point of the trajectories, we obtain this value C of AT. Then we can build the dataset. So from one part, we can build the input sequences. directly from the states of from the aircraft states of the trajectories, and we can build the output matrix, the target output, by taking the maximum of the complexity in each area. And then when we have our data set, it is split between the training set and the validation set, such that we can train our encoder-decoder network and then validate the train network. So now I will present the results of this framework. So here is an example of results. So this is the matrix, an example of the matrix HT. So on the left, we have the prediction of the network, and on the right, the true value. So this is the value 40 minutes. So this is the last value of the generated sequence in 40 minutes in the future. And so this is an example from the training set. So from an example that the network has used to train its parameters. So here we can see that, and so is the scale, the color scale is simply the value of the complexity in each area of the space. So we can here see visually that the network was able to learn to predict the complexity. Here we have so the same thing, but using an example from the validation set. So here we can see that the network struggles to really predict the true value, the true matrix HT. So we introduce a little trick. So simply, instead of using the raw data set, we smooth the data using a 3x3 Gaussian matrix, such that the data are more smooth and so easier to learn for the network. So using this smooth data, we can here plot the absolute error on the validation set. So we have 200 examples in the validation set. And here we plot on the left the absolute errors without the Gaussian smoothing, and on the right, the same thing, but with the Gaussian smoothing. So here, on the horizontal axis, we have the absolute error. So the complexity has been scaled such that the maximum complexity in the area, in the airspace, is equal to 1. And what we can see is that, so yes, another thing is that we have removed all the zero values, since in fact most of the error will be zero, since most of the airspace has no aircraft. So we have removed the zero value, and we only consider the values where there is a non-zero errors. So what we can see is that without the Gaussian smoothing, there is a lot of errors that are quite high, with a mode that is above 0.5, and even errors that are above 1. While when Gaussian smoothing, the errors are really centered around 0 and quickly decreasing. So we can compute the mean absolute error, and we can see that with the Gaussian smoothing model, we achieve mean absolute error of 0.08. So here we have an example taken from the validation set with the smooth data of the predicted matrix on the left and the true matrix on the right. And we can see that here the network was able to generalize well on the validation set and to predict the complexity in each area of the airspace. So to conclude, in this work, our objective was to predict the air traffic congestion in a time horizon of 40 minutes by combining 3 approaches. So the air traffic flow prediction methods, definition of congestion relying on an interesting complexity metric based on linear dynamical system, and machine learning techniques, more precisely encoder, decoder, LSTM. And we are obtaining encouraging results with the framework using a dataset that has been smoothed. So here I have listed some potential applications and future work. So this model can be used to provide information to the flow management position to improve decision making. It can also be used as an input to a bigger system that will aim at mitigating the complexity to bridge the gap between the FMP and ATC through the EAP concept. Another important aspect is the quantification of the uncertainty in the prediction, since if we want to deploy this tool, it has to be accepted by the controller. So there is a need to be able to quantify the uncertainty in the prediction, and to be able, the model should be able to evaluate if its predictions are reliable or not. And there is also discussion is also important in the certification perspective. Also, we can refine the model. So, for example, it could be possible to use other type of networks, such as transformers that can process time series or graph neural networks. And it should also be possible to consider a classification task rather than a regression task, because with classification tasks, it is easier to evaluate the performance of the model with several metrics. And it could also be possible to use historical data rather than simulated data, and consider other features such as weather data, in particular wind and temperature, that has a great impact on trajectories. And finally, another approach could be to predict the estimated time of overflight to selected waypoints that are well known to be the location of hotspots, and to use these predictions to compute a measure of complexity rather than predicting the complexity in the full airspace. So this concludes my presentation. Thank you for your attention, and I can answer the questions.
Thank you, Loic, for this wonderful presentation. Quite interesting, and lots of useful mechanism models you have brought together to bring some good insights into this interesting topic. So there's a question from Craig, and he's asking about the decision support perspective, the decision support system for the ATM. So he's asking, Craig is asking, how would you translate a prediction of high complexity to a recommended action by the traffic manager or by a controller?
So this is a question about the mitigation part. So
yeah, okay. So this is about how do you translate the prediction that's been of a high complexity to a recommendation.
So
like how an air traffic controller or air traffic manager is going to interpret what the model has suggested.
So
in terms of complexity.
So yes, a first step should be just to provide this information to the flow management position that can, and then it can use this knowledge that there will be a hotspot in 40 minutes to change this configuration or to enact regulation. And then for the mitigation part, so I haven't investigated that, but we can use an optimization algorithm that can provide actions and then use this framework to see if this action really reduce the complexity.
Right. Okay, I have just two clarification. Actually, I understand how you did the intrinsic complexity metrics and how you define the congestion and the encoded decoded Lstm network. One thing I didn't understood was the air traffic flow prediction part. So can you explain or elaborate a little bit on your traffic flow prediction method, or is it a method you took from the literature and fed into the Lstm model?
So, the idea of air traffic flow prediction is to, rather than focusing on predicting a single trajectory, is to predict flows on the whole airspace. So there is very different approaches. So some relying on networks and defining flows on the edge of a network. But here I simply model the airspace with this grid and then predict a value of this complexity of the traffic in each part of the grid. And so there is other similar work that have a similar approach, but they are just simply predicting the traffic density in the airspace. And so we can in air traffic flow prediction, we can predict the traffic density in an area, but also in an air route or above specific waypoints.
Right. Also, can you elaborate upon what are the various uncertainties that you are planning to quantify in your prediction model to make the prediction better?
So the uncertainty is the uncertainty of the model of the neural network to the quality of its prediction. So the idea is to create a network that is able to detect when, for example, when the data are too noisy, or also to resist to adversarial attacks. So this is really the uncertainty from the neural network parts. And then there is also uncertainty from the trajectories that are due to, for example, to weather data. So here, a possibility is simply to enrich the data with their information.
Right. Thank you so much. If there are any other questions, please feel free to post it on the Q&A box. Also, you may later on send the questions to Loic. Please CC me so that I can keep a record for the seminar purpose. And if we do not have any further questions, then we can close this session. I think both the presentations were very interesting from Ramon and Loic, and some very interesting perspective on air traffic flow as well as congestion prediction. Thank you so much to our presenters and presenting their work in the ATM R&D Seminar 2021. And I look forward to your continued contribution and cooperation in that. Thank you so much.